Okay. All right. So we're going to look at how we can represent at first different sets with Venn diagrams and different set operations before we get into actually filling in the Venn diagrams with elements. So first, this is explanation. That's in your notes what a Venn diagram is and created by some guy named Venn. So it's capitalized because it's a man's name. But if you have a Venn diagram, the box will represent the universal set. Are we good morning, Gabrielle? Where did I put that? Oh, it's over here. You checked off. Sorry. So nothing exists outside of the box. And then any subset, any set in a Venn diagram will be inside the box because it has to be a subset of the universal set. Some of them may overlap each other. Some of them will not overlap. I don't think we talk about mutually exclusive in here and stuff like that. That's more of a probability thing, but am I rambling? Somebody say, stop rambling. Yes, it is. It is recording right now. So if you were gonna, so all we're gonna do is shade these Venn diagrams for what it's talking about. So set A is the circle, right? So if you're gonna shade to show set A, you just shade that entire circle. So everything inside that circle is part of set A, everything outside of it is not. So here, a complement, you would shade everything outside. This is A. And then a complement. And I'm not going to shade these great for time constraints, but you get the idea, I hope. So you'd shade everything outside. Null set in a Venn diagram is nothing, so you wouldn't shade anything at all. It would all be just blank. And the universal set is everything, so you would shade the entire thing. So if your final answer when you're done has the entire thing shaded, then you'll know that's the universal set. And when you get done, if nothing is shaded at all, then that's the null set, and so forth. So those are just the four basic ways to shade a Venn diagram when there's just one subset inside the universal set. All right, so when we start talking about two subsets and two subsets that may share something in between them, they overlap, right? A and B, they could have some intersection. If you just want to shade A, you would still, A is the entire A circle. So you would shade all of A. So if you had three sets there, you'd still just shade the two. B would be shading all of B. So anything inside of those two areas, when you have two subsets that overlap each other, then you actually end up with four different sections of the graph, right? The outside, the A only, the A and B, the B only, four different areas. So one of the intersection is the little, what I always call the little football looking area. Intersection is where they both are. So that's the intersection area. And the union of two sets is the two together. So it's both sets together, including the intersection. So when you union two sets, both of them together. If you just have a complement, remember that's everything outside of A. So even if there's another set, you still, like here's your A set, you still shade everything that is outside of that circle, including the B part that's not. Yeah. So that's A complement, everything outside of A. And then subtraction is when you take set A and subtract out anything that's in B. So A minus B gives you that little crescent moon shape. That is the what is also known as like A only. Oop, went outside the line a little bit. Sorry about that. So if you wanted B only, you'd do B minus A. So just that little section there. Any question on those? So again, these are just your basic shading before we get into doing a bunch of different operations and stuff like that. You'll see what I mean. All right, so you can use Venn diagrams to prove that two statements are equal statements. If they're equal statements, they will end up with the exact same shading. So if you're going to prove they're equal, you first take one Venn diagram, do B minus A. So B minus the A part would leave you just the crescent moon part. There. And you'll see on the assignment and on the notes that I have this where it says working. This just helps you get an idea of, um, like I said, there's 4 sections, right? So your working area might be where you're making marks on and stuff, but then this will be the actual answer. They're the same thing. So like A complement is this area and this area, right? And then B is here and here. So where do those two intersect? It's where I marked both of them with X's, right? So the only intersection is that part there. So it's here. So like I say, that's just the working model over there to get an idea if you need it. If you don't need it, don't worry about it. But now, are those two equal sets? Yes, because they're shaded exactly the same. And that's it. Questions on that? Might be easier to do these with pencils so you can erase areas if you figured out you didn't shade them. So we talked about this yesterday, that A prime, oh, I didn't tell you that. Like this is A complement. A lot of people will say A prime. It's just a set notation term. So if you hear me say A prime, I'm talking about A complement. But A prime intersect B prime is the same as A union B prime, right? We talked about that yesterday, that those two are equal as long as you flip the sign. Well, you can show that with a Venn diagram. So to do A prime intersect B prime, A prime is here and here. B prime or B complement is also on the outside and there. And where do they intersect? Well, where I have 2 X's. So that is all of that. So for this one, A union B is here, here, here. So A union B complement is where I don't have X's, which again is outside of everything. So since the diagrams are shaded exactly the same, they are equal statements. So those two are equal statements. And it's some dude named De Morgan figured these out, so they're called De Morgan's Law, and talked about them yesterday, but there's two of them. And as long as you have the prime on the outside, so in this, like if I said D prime intersect F prime, what does that equal according to De Morgan's law? Well, you would bring this in, and the not would make that D, and then you change it to union and F prime. So that's the idea. So this law, even if one of them is the not, when you bring a not, two knots make a regular. The complement of the complement is itself. All right, so then we start getting into three subsets, and that's three circles. So there ends up being 1, 2, 3, 4, 5, 6, 7, 8 areas that you could end up shading in. So again, if you're just doing B, you would do all 4 areas that B is part of. So anything in those 4 is part of the set B. A intersect C is where A and C are both. So make sure you get both of those, and it's still that football section. Doesn't matter if B is not part of the sentence, it doesn't matter if it's in B or not. You're just looking at those 2 circles like it's a 2-circle Venn diagram. Just like here, if it's only one letter, then you're just looking at a 1-circle Venn diagram. Ignore everything else. B union C is all of B and all of C together. So it's there, there, there. So it's all 6 of those areas. Anything that's in B or C or both. So again, since it's just the 2 letters, it's like having a 2-circle Venn diagram. Just ignore the A circle, and union is always both of them. C complement, if this is C, it's anything outside of C, including the universal area that's not a subset of anything. So C complement is everything on the outside of that C circle. And again, just like a single circle Venn diagram, if you only have C complement, ignore the A and the B. Hopefully you get the idea. Pretty awesome drawing, I know. All right, so when you start getting to 3, you have to look at all 3 together. And remember, you can do, I didn't do a working on this, but you can do 2 at a time or look at all 3 together. Where does A, B, and C all intersect? Well, that's just that middle shape there. Everything in this area of the Venn diagram would be in set A, set B, and set C. But if you're going to union them all, then that's everything, as long as it's inside one of the 3 sets. So the union is all 3 sets together. A, union B, union C. There you go. So those 2 are pretty basic. Those are your main 2. If we do anything besides union them all together or intersect them all, then you need parentheses to show you what to do first. So this is C minus B intersect A, doing the B intersect A first. So B intersect A are these two. So then you're going to take set C and you're coloring everything but what we X'd out. So it ends up being all of that. Like I said, the working is just to get an idea. You don't have to use it if you don't want to. And then do these nicer than I do them. But that's the idea with the shading. Questions? Keep going, just a couple more. So C minus B would go first since it's in the parentheses. So C, take away all the B, are these two areas. And then you're going to union it with A. So even though this section of A got taken out of the C minus B, it's going to come back in because it is part of A. So your union, all of A, which is those, all of A gets union with that C minus B. So I'm going to color everywhere where there's an X. So that's all of A. Was being unioned with wherever the C minus B was. So that's it. Just missing that. So yeah, just because the parentheses takes a piece out doesn't mean it can't come back in from the other statement. So A intersect B is A intersect B are these two, where A and B. Where that intersects not C is here, 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 here. Yeah, the outside is not, and then those three areas. Intersection is where I have two X's, so the only place that intersects is just this little piece up here. It's like Star Trek shape for the new Space Force. That's it. So again, if you like the working area, use that. But if you're all right without it, some people do really well with these, like a puzzle. Some need a little more practice. All right, so this same thing, we have three. If I can show that this and this have the exact same shading, then they're equal statements. So first, C minus B are these two areas. A, here, 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 and here. So where do they intersect? Just that where two X's are. And this one, A intersects C, those two. B complement is everything outside of B. And where do they intersect? Where the two are. So it's also that exact same area. So yes, they are equal statements. Yeah. I think that might be, yep. So that's it. So hopefully that'll be a good start if you come back to where are we? The assignment. Just same thing. All you're doing is shading. If you can't print this out, you can draw those over and over. Not too bad. Prove that those two are equivalent. Remember, the working is just that. If you do that or not, doesn't matter. It's the solution that's important. If you want to use that working piece. So I think that's it. So try those and also catch up on other stuff if you have not. Stop sharing.